Say it again.
I'm gonna switch the outlet. Is that okay?
You gonna switch here?
Yep.
Oh, this is not my computer.
That's not your computer? Well, I take that as a yes. No. Oh, it's this.
It's this, yeah. I would suggest probably somewhere else where this person cuts themselves. Is that email?
Wait, we have another
Yeah.
the model is not me. There. Wait, let's do first the mic. This is charging. Because we have one please hold there. And we're going to need this one closer to us.
Wait, can I switch?
Okay, good afternoon, everybody, and welcome to this other Thursday together at BrIAS, at the Brussels Institute for Advanced Studies. And it's a pleasure for me to introduce you to this new afternoon together. And in particular, I want to start introducing the first speaker, that is Eduardo Camacho from the University of Seville. It's really a pleasure to have him here with us. So Eduardo is one of the most well-known researchers in automatic control in the world, I would say. He's one of the reference person for what concerns constraint control. Most of us have learned constraint control from his books and his papers. He's really one person that many of us in our community look up to. And furthermore, he was also one of the pioneers for what concerns the usage of model predictive control in solar systems, and this is what he will introduce to us today. So just some short mention about the career of Eduardo. He has been, I think, most of his life at the University of Seville, where he has built an enormous group of research. He has trained a lot of excellent researchers that then have become professors themselves and have created other groups around. He has, in the last few years, he has also been awarded with an ERC Advanced and very recently with an ERC Proof of Concept. I could go on for quite a while because his contribution in our community is enormous, and moreover, he has also given a lot of contribution to the various societies. Just my memory organized a CDC and an ECC in Seville that seemingly is still quite famous among the people who were present, and many other things. So I will not continue with this introduction. It's my pleasure to really give him the stage, and thank you for coming here.
Okay, thanks, Emmanuel, for those kind words. Everyone noticed that you're my friend. So I'd like to thank also BrIAS and you again for, and Annie also for the invitation and the opportunity to be here. So I'm going to talk to you about model predictive control of solar plants. So I should say thermal solar plants. So, and this is the outline of the talk. I first tell you about a little bit about thermal solar plants. Then I speak about how MPC can be applied to thermal solar plants. Well, I'll describe some control experience that we have with commercial plants. I'll then speak about OCONTSOLAR, which is advanced grants that I was awarded by the European Research Council, and finish with some concluding remarks. Okay, so this is what's a parabolic through plant. You have the collectors here. Usually, this is a collector. Usually, they have some, let's say, 4 collectors. And all this is a loop, and they have many loops, not just 4 loops. Basically, a 50 megawatt plants have something like 90 loops, and the big plants like Solana, they have something like 808 loops. So those. Okay. So you heat up the oil in the field, and then you generate steam, and for that steam you move some turbine. You can also have a boiler, a gas boiler. It's used for, let's say, transients when you don't want to stop the system. You have clouds. And also you can, because the oil that circulates through those pipes can freezes around 70 degrees Celsius. If you have a few days without sun, you may get run into problems. So you can also heat up the oil there, and then also you could have a storage system. Well, not this kind of storage system. Usually the molten salt base storage system that you have. Okay, so that's basically. So the big plants are concentrated solar power plants. There are two kinds. One the tower, and the other one is solar troughs, which is this type. The big plants are all solar troughs. You know, you run into many problems when you want to do big plants just with a tower. Okay, so the idea here, this is from an experimental station. This is from a real one. So the idea is you have this parabolic mirror that tracks the sun in one axis and then focuses the sun irradiance in this pipe that goes there, heat up an oil, heat transfer fluid, and that is up to normally they receive the oil at the cool end around 300 Celsius, and at the hot part is the temperature goes around 400 or 394 degrees Celsius. So control problems in solar plants. The first one that everyone thinks about is collector movement. Okay, how do you track the sun? Well, that's slow. Actually, very simple. You just compute where the sun is. Okay, and that's usually done by PLC, and you have very good equations for that. And then you may also have a fine-tuned mechanism on top. But that's well studied. That's not really a problem. The problem comes when you're trying to control the thermodynamical variables which are involved there. And why? Because you have very rich dynamics. You have PDEs, the time, non-linearity. You have very high disturbances, and this is done in closed loop most of the time. So when you look at the film, you want to control the outlet temperature, the hot oil temperature at the end, and then you do that by manipulating the oil flow that goes through the pipes. Okay, so you have severe perturbations there. The main one is actually the solar radiation. It's that can drop, can goes from 900 degrees watt square meter to something like 100 degrees square meter in a few seconds. Okay, so you have a problem there. Also, the temperature and the inlet or temperature disturbances. Okay, so if you look at one of those pipes, they have a metal pipe, and usually with painted in black, basically. But and then you have a glass cover with a vacuum in the middle to minimize the thermal losses. Okay, sorry about that. There's one things I don't want to. Okay, so this, if you look into the heat equations, the energy equation, you have this for the metal. It's where you have that Tm is the temperature of the metal, and then this is the solar radiation going in. These are the losses. Ta is the ambient temperature, so you lose some of that heat, and this is the energy, which is or power in this case, which is transmitted from the metal to the fluid. Okay. Then again, for the fluid, this is the equation that you have, but in this case, we also have a derivative with x. Okay, so it's a PDE system, as you can see, and because of that, this system have some challenges for controlling. One, I think the first one is that the energy source is not a manipulated variable, but a disturbance. That's the main one, because normally in all power plants, the main manipulated variable is a sort of primary energy source that you're injecting into it. Okay, if you want more gas in your car, if you want more speed in your car, you press the accelerator, and that increases the amount of gasoline getting into your carburetor. Okay, that's normal way. Okay, so but in this case, you are controlling it by the load, the system load. Okay, so it will be, as I said, tell my students, you're trying to control the speed of bus. Okay, instead of doing it with accelerator, you are doing it by throwing passengers. Okay, getting rid of some of the load. So that's part of the difficulty. Now the second one is the complex dynamics. As I said, non-linear PDEs, the time, because there's long pipes, and then never at steady state, because solar radiation is changing all the time along the day. Also, you have constraints. Not only you have constraints, but you are normally operating close to them. In control, you say, well, constraints are far away. I try linear, and if I hit one of the constraints, just clip it, okay? But when you're operating close to the constraint, because you want to operate close to the constraint, because that sort of temperature, we're talking about 400, that's a bit on the low side for steam generation. Okay, so you want to go high on that. Also, when you're storing energy, so you're operating close to this. And then deciding the operating mode is part of the control system, especially when you have storage, energy storage system. You have to decide when to send your hot oil to the storage, or what amount of hot oil you're sending to the storage, how much, what amount you're sending to production of electricity. Okay, so there have been many people who have been contributing to, sorry about that, to, but this seems to have a life on its own. I don't know what I want to do, I'm sorry. So there's a list of people that have been contributing to this problem, okay? And they apply many control techniques to the system. Well, of all those techniques, sorry about that, I should say that the model predictive control has been, I think the best results have been obtained with model predictive control. So how can you apply model predictive control to solar plants? At various levels. You can apply it on the sort of power computation with a horizon of 24. You have to decide how much you're going to produce every hour, and how much you're going to store. Okay. Then, once you decide that, you can optimize also the set points. Okay, try to do that the optimal way, and then shorter horizons, until like 30 minutes. You can also you use model predictive control to control the main variables. So to give you an idea of those, okay, when you have at the top level, the planning power, do you have this type of equation that's delivered power, and this is the price. Also, you may have some price if you don't deliver the contracted power. Okay, you have a penalization there, and then also if you have a storage, you want to also to maximize the amount of energy that you're storing in your tanks. Okay, then you have that's power that the sun is giving you. So that's is equal to this equation. It's basically the delivered power plus what you're storing, sort of plus what you're storing minus the energy that you are delivering, that you are getting out of it. And also, if you have some equation where you can model how the power in the storage place deteriorate with time, okay, and some constraints. Okay, but this is it can be a linear program. Okay, not a very simple linear program, really. But you have to suppose what this sum is going to do, okay, for the next 24 hours, and you can do that very clearly in sunny days. No problem with that, because you can predict exactly what the solar radiation is going to do along the day. So you have to compute the delivered power, maximizing that type of function. And then you do this with every hour, and with that sort of decreasing control horizon. Okay, if you're planning up to the next day or for a few days. Okay, so to give you a flavor of that, that's a work that we've done with And it had to do with using multiple scenarios, MPC, because it's an uncertain problem. You don't know what, and you have two types of uncertainties. It's the power production on the sun, and also on the electricity market prices. Okay, you don't know. You may know that for the next 24 hours, but if you're doing a control horizon, you're using tests, and you have longer horizon, you don't know exactly what the prices are going to be in 48 hours. Okay, so well, for that we did a collection of scenarios. Okay, and okay, that's what I was saying before. The electricity prices are now 1 day ahead. The prediction of future prices based on current costs and the sort of last 10 previous days' prices. Also, you have uncertainty there on weather conditions. So for this case, we were using a prediction horizons of 4 days. And also, this is what I was talking to you about. In the next 24 hours, you know what the prices are going to be. But from there on, you had to play with different scenarios. Okay, so the same thing for what's the weather going to do. Okay, so also we sort of train with a sunny day, with a partly cloudy day, and also with a very, very cloudy day, with an overcast day when you cannot produce anything except for some peaks. Okay, so that's what we did, and we show that we have some gains using this type of scenario. So with the, let's say, normal way of operating it, without taking into account the different possible scenarios in the long run. Now let's see at the optimization level. These are basically how the main variables are related. You have all the solar radiation and the reflectivity. You also have the day and hour, because depending on that, you get more or less power depending on where the sun is. Okay. Then with that you get the solar power, but then you get a net thermal solar power, which is that minus the thermal losses. Okay, the thermal losses depending basically on the temperature. If you're operating high temperature, you have higher losses than when you're operating at low temperatures. Okay, and then the sort of depending on the flow, you get an outlet temperature. Okay, if you have smaller flow, you get higher temperature, and the other way around. But if you have higher flow, means that you're getting your pumps are operating at higher speed, so you're spending more in energy in pumping there, and that's not negligible. So for a typical, we're talking about 8% of the production. I mean, for a 50 megawatt plant, the pumps are dimensioned to be 5 megawatts. Okay, just the pumps. So they can't spend an amount because you have oil. Okay, even if it's hot, it has a viscosity, and you send the oil 4 kilometers away. So that takes an energy. Okay, so well, after that, that's what you want to minimize. Okay, really, and then you may have storage. So this is a dynamical system, but you can, let's say, optimize, because if you're fixing your next point for the next 2 hours, you have some time for computing it. So that's not a problem. Okay, now for the third level, let me talk to you about this platform in Almeria. That's an experimental station that's been there since the first, or after the first oil crisis, and there are many different plants there. These are tower plants. This is another tower plant, and these are solar trough plants. Okay, and this is another solar troughs, but in this case, is for producing steam directly. So, and even they have a solar oven there. So many. Okay, so in these plants, for a model of these plants, we show that you could get something like, well, this is only a small plant. Well, at the time, the first time I saw it, I thought it was huge, but now I think it was almost a toy plant. Okay, But, okay, so extrapolating it to a 50 megawatt plant, you can gain something like 20 megawatt per day, which is the price of electricity now, or even if you are, when you put the feed-in tariff, that's a respectable kind of money. Okay, so let me see. Okay, actually, this, we had to fight with the reviewers to get in this paper in, because one of the reviewers that obviously was working in one of those plants, he said, no, it's not, that's impossible. The best way of operating it is going to the highest temperature, and we showed him that that was not the case. But we took some time to show this reviewer that this was not the case. So it means that, why it's not the case? Because if you're operating at high temperature, you are reducing the consumption of your pumps, okay? Because high temperature means less flow and also less viscosity in your oil. You're reducing that, but you're losing energy because of that. So it's not very clear. You have to do some numbers to find out which is the best way of operating it, depending on the point. Okay, so they're regulating the third level, which is regulating the main variables. We done a few things there. One of this actually, I think, was the last sort of controller that were tested in that experimental station, because they did, okay. So I'm very sorry about this. I don't know how to. Okay, so what we use is uncertain filter, more or less, to estimate the temperatures along the pipe, okay? And with that, you will get a better control. So these are the results on that particular plant, okay? It behave very well. And in case you say the temperature drops, it drops because you cannot do anything. The solar radiation is dropping suddenly, so you cannot do anything like that. And this is, again, the same case, okay? But the nice thing about this, solar radiation drops, but then it goes and pick it up without big oscillations. So other type of controller, if you don't put a model predictive controller there, will pick up again the temperature, but will oscillate a lot, will go very high. Okay, so the MPC helps in because it's looking forward, and it will try to stop before it oscillates. Okay, so this type of controller have been applied to a lot of 13 to 15 to 16, no, 17 actually, because 17 plants, and we designed the controllers for them. I even helped to in the implementation on. And those are in Spain, something like three here, 13 in Spain, about 3 in the US, 1 in South Africa. Okay, and I cannot give many details of those development because they are non-disclosure agreement signs. Okay, so to give you an idea about those plants, these are 3 different 50 megawatt plants. Okay, so if we zoom into this red rectangle, that's what we get. Okay, this you can see the collectors here. To give you an idea of the size of this plant, this is a car, okay. These cooling towers. Okay, this is in Caxo. And okay. And this is to give you a nice idea. This Caxo, this is a 100 megawatt one. It's not the big.
In 400 meters, you will arrive.
Okay. Okay, well, okay, so, okay, I'm sorry about that. Okay. Well, when applying MPC to these real plants, we soon realized that it's not academic exercise. There are too many constraints on it, and things that you have to look at. And basically, the solar field cannot be operated independently of the steam generation part and the turbines. You have to take account the steam pressure, the aperture of the high pressure valves in turbine, also the superheating, power production limitation, temperature gradients limitation everywhere. So there are many limitations, many constraints everywhere that you have to take into account to plan that. And so this is a case, this is Mojave plant. Mojave is in California, okay. And this is a temperature, okay. This solar radiation is in yellow, okay. So it's, now here the flow is already at the minimum, so it means that to get the sort of temperature that they want, you have to reduce the flow. And in this case, it goes up because trying to reduce the the gradient, temperature gradient in the field. Okay, so anyway, so this is another case about the same thing. Okay, but again, we have some clouds here. Okay, but of course you don't have, even if you have the minimum flow, you cannot keep the temperature, so it goes down, you don't have enough energy. But as soon as the clouds goes off, it sort of recovers softly instead of going on oscillating all over the place. Okay, so what I like to now to speak to you about is about the grants, the advanced grant from the European Research Council, or optimal control of thermal solar energy system, is related to that, but let's say more ambitious objectives. Okay, so the idea is that in the big solar plants, okay, you may have clouds covering part of the plant and not the other, and to control it properly, you need to measure the energies that you are receiving. So you need to measure the direct normal irradiance, okay? And you do that by using this type of equipment called a periliometer. So a periliometer is basically this tube, okay? And then at the end of the tube you have the sensors, and you have to point that to the sun all the time to measure, okay, to the center of the sun. So you don't, this periliometer, this costs around 3,000 euros, but just this tube. Now the pointing station can be around 25,000 euros, not 25 euros, 25,000 euros. So these are expensive equipment, and you may not install those all on the plant. It will be too expensive. Okay? So they normally have one or two of these. So they measure the solar radiation in one point. So our idea there was to use mobile sensors mounted on drones or ground vehicles, and then to measure especially measure the solar radiation on the plant. Okay, so that's one of the problems was that. One of the problems was given this type of measurement system, how to find an estimation of what the DNI was around the plant. So in our case, we have a fleet of mobile sensors. We have 3 of those. Okay, so you can see you can see the mechanism there to a pan and tilt and as a small sensor too. And then also we soon realized that we will be better using also this type of hybrid drones. We built this prototype. Again, you can see here on the nose of you can see also the mechanism for tracking sun, also ground vehicles. Okay, but with this type of drones, we could have more speed and also we could have this drone more time on the air, okay, than the other one. Okay, so that's the idea. Okay, this is the type of sensor that we're using in this case. And what we wanted to avoid problems of collisions, etc. So what we're doing is to fly the drones at different height, okay, like they do with the planes. It's a case of, and then you in this case, in this work in particular, okay, we have what we do is fly one of the drones around. We have certainty about the places we have taken measurements, okay, and then places where we don't know what's the solar radiation is there, but we can somehow suppose using some different type of techniques. Okay, well, and then this is another one where the next waypoints is computed, then taking into account what area has not been measured, okay, and then without that, well, again with predictive control, okay, and well, sort of if this is the previous direction, we sort of look around to which is the best way to do that. Measure a function that takes into account what's the trajectory, next trajectory is going to move up, how many points are they going to visit where measurements have not been taken recently. Also, we have the wind into account because the clouds move, okay? So we, again, consider the clouds moving to do that. With the clouds, and more than the clouds, the shade on the ground, which is interesting. Okay, for example, this is an example of using, in this case, 3, 5, or 7 drones. This is a simulated sample with this, one of those algorithms. And then you can see here the mean error. And again, it's also the proportion, if you look into proportion or area proportion, where the error is bigger than 100 watts square meter. Okay, so that's getting reduced. And on the other side, we have the area where the error is less than 10 watts square meters. So the area of this one grows with 3. So you would like this black one to go down quickly and this brown one to go up quickly. So obviously, if you use more drones, that's what you have. Yeah. But there's not much difference of using 5 or 7 for this particular size of what we were doing. It was done for one plant around 1 hectare. Okay, so something else that we're doing here is to using this was not original in the proposal. We found out that we could use the sky camera because most of the plants have sky cameras. Okay, they're looking up to decide where the clouds are and where they're coming. So we're looking into that, really. So, well, so using standard image processing techniques that we've tried to find out where the clouds are, to identify them properly, and then also optical flow, okay, and then reduce that optical flow to transform it to optical flow on the ground, okay, while using using standard techniques. And then, well, one problem was the height. Where was the cloud? How high they were, okay, and that can be solved using two stereo cameras. Oh, sorry, 2 sky cameras, okay, but they have to be something like 3 kilometers apart. We couldn't get that. 2 sky cameras. We had 2 sky cameras, but not to have it 3 kilometers apart was difficult to do. But in school there are some people that have a sailometer, so to measure in how far the obstacles on the sky are. Okay, they do that in looking vertically. Okay, so by combining both things, we could find where the clouds were, and from there we could project the shade of the clouds on the ground, which is what we're interested in. Okay, and then again, the next problem is once you have different measurements, how do you estimate the DNI distributed along the plant. Okay, as in this case, this is the plant. Okay, this is the power island where they have the power equipment. Okay, so these are the shades. You have some clouds there, and they get projected to the ground. So now, how do you estimate the? Well, one of the work that we did with that was a variation in inference estimation. Okay, and that's sort of the typical stuff. So we have posterior probability, then we use the nearby cells again to modify our estimation issues, the cells, and also regularization factor, meaning that the probability there decreases with time because you have not visited that cell for some time. Okay, and these are some samples of showing in this case. There are some videos there which are not showing for lack of time. Okay, so it's on simulation. Well, now the thing is how can this thing influence on your plant? Okay, so we have some simulations here of and then you have a couple of samples where you have one cloud on this field, okay, not on the other, and then you can see on the top field there is no problem. Okay, you have you don't have any clouds there, but in the bottom field, these are the temperature in the loops, and of course the clouds coming from one side to the other, the temperature is going down like that. It's a theoretical thing, but it means that you're going to have a smaller temperature here. It means that your flow is going to reduce. And if you reduce your flow, you're going to increase the temperature on the other side. Because if you increase the temperature too much, these type of plants have a defocusing mechanism. Okay, because over around 400 degrees Celsius, the oil that they have it starts to decompose to generate volatiles, which are also dangerous. Okay, so they have a security defocusing mechanism. So it means that when the temperature is very high, you are throwing energy away because of the defocusing of the part. Okay, so this is another case. We have a bigger cloud crossing like that, so you're affecting both of those fields. Okay, and then of course the cloud's bigger, you have more disturbances on the temperature, and the effect I was talking about before, meaning that you're also losing energy and you're not getting all the energy you're supposed to get. So, well, let's say now, let me see. Now the problem with that is that the way of controlling this is by manipulating the valves. Okay, but if you have in a 50 megawatt plants, you have 90 valves. So how do you control 90 valves? Okay, with a controller. Okay, so we say, well, that's too many. So we'll try to group them somehow. So, but the grouping depends on the situation. You cannot group them and then just forget about for them, because in the next hour, the groups that you have made maybe not make sense. You should have grouped them in another way. Okay, we thought about coalitional control for that. So the idea of coalitional control is grouping the controller, but taking into account the situation dynamically. That's the idea. Okay, so well, what a coalition? If you have a set of players, and they can be organized in groups. Okay, and each of the key thing on coalitional games is the utility function for which assigns a value to each of the coalitions. That's the way you form the coalitions, really. So the most famous one is the Shapley value, okay, to measure that. Okay. And so we have used that in many problems. For example, one problem is the task allocation of the robots. You have missions, okay, and you have a number of robots. How do you send the robots to a particular place? So again, it gets very complex if you have a lot of missions and a lot of robots, too complex of a problem. Then we say, well, we have to sort of break the problem. But again, it comes a dynamic problem. It's not a, so we use that for this type of problem, for task allocation. Then another, and then again for controlling the loops. Each of those is a loop. So if you have, like in Solana, 180 loops, how do you control those? It's again, it's a ridiculous problem, because also the bud affects the flow of the corresponding loop and all the others. Okay, too many variables and too complex of a system. Again, we thought of using collisional control type of thing. So what we do is clusters of loops. Not necessarily they have to be together. So you can have one collision here, or one element belonging to a collision here, and the other ones are very far away. No, not necessarily they are together. And now there are two problems there: how to make the collisions, the groups, and then once you've done that, how to control them. So for that, we've also thought of a sort of market-based clustering. So the idea here is to use a type of consider the oil as a commodity. Okay, so each of the loop, in principle, receives its oil, corresponding oil. Okay, but you say, well, if I increase the oil that I'm using by quantum, I can produce more power. So that's what you're ready to pay for that. And on the other hand, you have loops where you don't need oil really. You want to get rid of it. Okay. So you have also selling price for that. So what we do is adjusting the buyer, the higher buyer price to the lowest, and we determine the price in the middle. So everyone gains from that point of view. And those two form a cluster. They're ready to interchange oil in order to produce between both of them more energy. Okay? And now you can do that, repeat that another time. You have two groups of two. You can repeat that again another time, group of four, group of three. Okay, at one point you have to limit the size of the groups. Okay, so by doing that, that's a simulation, MATLAB simulation. So that's how the colors here represents the groups that they are in. Okay, and this is what's happening. Okay, you see, I think the next one is one. Okay, next one. So it's working from that point of view. But well, the problem here is even so, you for a smaller group, still is a complex problem from a computational point of view, because you're optimizing too many things. So we say, why not to apply neural network to this type to make it learn? And we also did that, okay, without losing too much optimality, losing all small fraction optimality. We could get, let me see, that's well, this is a basic idea to set of neural networks, one for forming the groups, and another set for controlling each of the groups. Okay. Now, so it's an example. Well, the interesting thing is the time. Okay. So this is it's a log scale here. So this is this is sampling time. Normally you can normally this type of system you can sample at 1 minute and you're all right. Okay. But if by using the, let's say, optimization type of approach, we have this type of times. By using neural network, we reduce the computation times drastically without losing too much performance. Okay, so this type of idea has been also applied in sort of simplification of those, not have been applied to the Solana plant. I was in Arizona. There's 280 megawatts electric, and they also have a test system, which means that really the solar side is much higher than that, okay, because they can produce electricity up to 7 or 8 hours after they lose the sun. And then again, instead of doing an estimation over all the field, we did an estimation of each of the sectors. They have 8 sectors. This is far northwest, far northeast, near northeast, etc. That's actually say it's working quite well. Okay, so that in September had to be something like 20 days in the desert in Arizona. Okay, looking at these things. Okay, and then also in Mojave, we have done the Mojave, the Alpha. Sorry, this is so Mojave, which is in California. We have on the Alpha plant 140 megawatts, 4 sectors, and the Beta plant, which has 140 megawatts, 6 sectors. So to conclude my talk, so well, MPC controllers are all been, I think, been very successful in this type of plants, basically because long delays. So, and then you can use some way of controlling the non-linearities. Also, always found that this control are always better than the best operator, always better than the best operator. And the producers increase from 0.5 to 2.5 depending on the operator on the day. And more else, the production is not relying on the operator's skills. Sometimes you get very good operators, and sometimes you get operators which are not very good. And then no constraints violations, and it takes care into that. Very short payback periods. For OCONTSOLAR, well, we think that better control and supervision can be done with better information and valve control. The simulation studies have shown gains of around 5%, which is a significant amount. And also have been some proof of the concept in Solar and Mojave. That's all. Thanks very much.
Okay, so thank you for this interesting talk, and now it's time for questions.
I will start with one question that actually I wanted already to ask you another time that you gave a first version of this talk. That is, when you arrive at the end, you show improvement between 0.5 and 2.5%. That for many applications, it's not much. In this application, I imagine that instead it means a lot of money. Could you give us some range?
Money. Well, there's one of those, for example, 50 megawatt plants. If you have something like, and there are 10-hour operations a day around that 50 megawatts, we're talking of 500 megawatts hour. Okay, so if you depend on the prices of the electricity that they are being very costly. Something that suppose that you have I've seen prices of electricity like 300 euros megawatt hour during this time. I suppose that you have 100 megawatt hour, so we are talking about 500 times 100. Okay, so that's one production a day. So that's how much? 500 times 100 is 50,000 euros. So 10% can be 50,000 euros per day. So it's some gains. In the bigger one, you multiply. If you have, instead of having one, you have 140 megawatts, like in those two Mojave plants. You multiply that by 3 in each of those, or 6 in both of them. So by the end of it's some not negligible. That's not as much as in the petrochemical industry, but it's not negligible gains. Let's say, I should say a short payback period, considering what those people have paid us for getting those things.
Okay. So thank you for the talk. I was quite surprised to see a coalitional game theory analysis of your model, of your setup. And so I do game theory and I'm interested in this stuff. So what you mentioned Shapley value. So it looks like you're looking for fairness measures, how to distribute the value. And I want to know what kind of measure gave you the best results, or what you're looking for. And then if you have a problem, also stability, because in coalitional games, coalitions can break.
Okay, yeah. The first thing is that actually here, Shapley value is to redistribute the gains in between players. So it does not make much sense here, because you have only, let's say, one player. Okay? So, but in this case, I don't see any sort of value for that, for the Shapley values, and it's auto distribution type of measurements. And the second one is stability. Well, we don't just chain coalitions. We have different sampling times for coalition and for control. So we are not chaining coalition. Once we have coalitions formed, we keep that for some time. That's and then we are not playing with those.
Is there an optimal way to form coalitions? That's what you're, sorry. Is there an optimal way to form coalitions?
Well, let's call it suboptimal. I wouldn't say it's optimal. Okay, you have depending on what approach. We have tried many approaches for this type of problems, but one of the approaches was to, on top of that, you decide, you analyze the whole thing. Okay, you decide, well, this coalition. So you evaluate how that coalition is going to work, and you optimize a function. Okay, and then so you have a value for that coalition, and then again you get another coalition and do the same thing, and you have another value. So at the end, after analyzing a number of coalitions, you may decide which one is the best. So I shouldn't call it optimal, because you have to check everything, and that's
very interesting. Yeah,
not feasible.
Thank you.
Thanks for a nice talk. I have a couple of curiosities. The first one is you mentioned this MPC strategy that considers 96 hours to produce through the solar plant. But what happens in terms of efficiency or within the MPC during the night, for instance? Because we know that we have to keep flowing the oil, and also that you have to keep it warm, because you detail that below 70 degrees it becomes solid.
Okay. Yeah. Well, you have to do that. But at nighttime, they reduce the flow considerably to basically have to do with the Reynolds number. Over higher Reynolds number, you got a turbulent flow. That's what you want your pipes when you have the sun, because otherwise you will heat too much the oil close to the tubes, and it deteriorates. So when running normally, you want a turbulent flow. So you have let's say, a minimum flow that you can have in the pipes. But at nighttime, is the other way around. You want a laminar flow. So it means that your oil is losing, let's say, less energy, because the one running close to the pipe will going to tend to have the equivalent temperature down there. And also, remember that those pipes have a glass cover with vacuum in the middle. So they have a good, let's say, thermal resistance, okay? So they have a low conductivity from that point of view, okay? But even so, it can happen if you have, because you're not because of various days without sun, because those plants are located in the desert, so that's not the case where they have a long periods with clouds. They may have 1 or 2 days with clouds, storm, but not all the time. Okay, but the problem comes when the summer system breaks, and they had to stop the plant because they had to replace one of the turbines or one of the steam generation units or whatever. So that may take a number of days, a month or a couple of months, maybe in some cases. In those cases, you may have run into problem too, and you need to circulate oil and then to. But even so, you have to be, I should say, a problem within the pumps, field pumps, because even if they don't produce steam, they may circulate the oil to avoid those type of freezing problems. Okay, and you say, well, what happened? Pumps break. Well, they happen in Solana. They have 8 pumps. No one. They have a number of pumps. But even so, part of the system can break.
Okay. My second curiosity is that since you mentioned the use of neural networks within the MPC, is it possible to include the knowledge of the best operators into the neural networks, not to create a black box model about the grouping, but also to include this knowledge?
It will be possible. I think it's that there are too many things happening in the plant. And then actually what we did was trying to do that, not with neural networks, but with our networks. So we were in the control room talking to those guys, why did you do this and why did that? But it's, you say that every day is a different situation. Yeah. So it's not, maybe you could do that, but I'm not that sure because so many variables and then they not always do the same thing.
So I also have a question. In a different life, I was working in prediction of production of photovoltaic plants, and there a big issue was that since they were located in the desert, you get a lot of dust on the photovoltaic panels, and it's hard to take that into account in the production models. Is this something you took into account for the mirrors?
Yes, we took it. We have, when you have your model, you have to specify what's the dirt degree of your whole field, depends on how you're programming it. And it changed, actually. One of the things that we saw in one of those control rooms was because we also designed for them a mechanism for defocusing, basing control instead of basing in an automata. It worked much better. But, and then we realized, it was during the summer, that the less effective loops were the one that was working better because they didn't have the defocus so much. Okay, so we said to them, well, you better don't clean them, just leave them because you have enough sun, enough energy. So if you clean those mirrors, they're going to defocus a lot. Okay, so it obviously affects because the reflectivity, one of those can go from 0.92 when they're very clean and very new to something like 0.6. Okay, which is like a 50% reduction of the reflectivity of the amount of energy that you're receiving. So they have a mechanism, that a cleaning plant. But even so, when you have a storm, all the reflectivity goes to the sandstorm, for example. I lived one of those occasions in Camacho. When I was in Camacho in South Africa, there was one day one of those storms, and reflectivity came down to something ridiculous the next day.
Okay, other questions from the audience here? Okay, if not, we have a question from Michel Quinar. Thank you for the nice and impressive talk. Determining a suitable model for control is often a difficult task. What is the complexity of the models you are using, and how do you tune model parameters in practice?
Okay, model parameters for control or for the model of the system?
Or,
to say?
how do you do model parameters in
Okay,
practice?
I can tell
Is
you.
the is the question.
I can tell you what we do. We have been working in the field a long time, and we have a sort of precise model, and we use that for precise non-linear model with a lot of breaking the pipes in a lot of places, and that's we use that as reality when we are testing our controllers. I should talk to the camera maybe. Okay. We use that for as reality, okay? And then from there we develop set of linear models and different operating points. Really, we do what the people in the aerospace industry that with controllers. Linear controllers designed in a number of different points. Okay, so that's what we do. How do we estimate that? Because we have a non-linear model that have been tested against a lot of data coming from the real plant. So once we are happy with that, with the real, let's say, non-linear model, then we use that model to estimate the parameters around different operating points.
Okay, so I see that Michelle is typing here on the chat. Maybe. Yeah. Okay, thank you for the detailed answer.
Okay. No, thanks to you.
Okay.
Thanks to you for the question.
It was a follow-up of the question, but okay. So if there are no other questions, let's thank again Eduardo for the nice talk.
Thank you.
And we have 15 minutes of break. Okay.
right. Welcome back, online friends and real friends in the real physical world. Just first, a shameless announcement of what we do. The nice 2 forums coming up very soon. So we have first the forum on human-robot collaboration on April the 26th. In the new fancy shiny BrIAS offices and spaces. So please come. You will get to have a lot of knowledge about sustainable robotics in healthcare and production, with also different formats brought by Shirley Elprama and Anne Jacobs at the Baguette. Then we will have a very fancy and ambitious program for the BrIAS Forum. That will be the last forum of the whole BrIAS Fellowship. It's the War, Peace and Robotics, and it will be in a beautiful venue, the Hall des Marbres at ULB. It's in one of the historical buildings of the university. And you will get to have a very nice 2-day program orchestrated by Emanuele and his colleagues at SAS. So please register, don't hesitate to come and share the good news. So now it's my pleasure to introduce the esteemed colleague Ariane van der Walle at the BUDA VUB, the Business Development Academy. You might have noticed in the space immediately on the right the name Sustain. So beyond the buzzword, what is it? Throughout Europe, you have about 400 what we called digital innovation hubs. What is it behind this beautiful Euro acronym? It's places where local organizations throughout Europe create projects that have a specific aim, is to help the digitization of local organizations. So it's European money, usually shared with a regional actor, and what's the main purpose is to help specifically local companies, local organizations have a step up when it comes to digitization. And when you look at the nature of the European Digital Innovation Hubs, they vary greatly because each region has different needs, goals, expertise. You have, for instance, a very interesting European Digital Innovation Hub in robotics that took place a few years back that still exists now, where you could come with an idea, a general idea of how robotics could be useful to you, and then they would help you a bit set up the different steps. So it's a free service. Here it's targeting small and medium-sized companies in Brussels who are interested about using AI. And small and medium-sized companies represent 80 to 90%, I think, of the companies in Brussels, mostly one individual. So it's the majority of companies in Brussels, and here the service aims at different things that Ariane will explain very well because he's working on it. So it's an idea that you cannot use AI without also thinking about sustainability now. It's a lot of set of free services that Ariane will present. And so thank you for also doing the linkage with robotics. So the floor is yours.
Maybe just the AGMI would be fine. Okay. Thank you.
There you go.
Okay, looks good. Hello everyone, thanks a lot for having me. I am Ariane van der Walle, and I will be talking about this interlinkage, like Karel said, between digitalization and sustainability being the core topic I'm working on, and I'll try my best to now and then make a linkage with robotics to keep it relevant for you. Very briefly, I kind of feel a bit bad with introducing myself when an esteemed professor before me didn't even have an introduction slide, but my background is in bioscience, engineering, and in sustainability science. I studied these masters at Ghent University and in Maastricht, and I'm currently a PhD candidate at the VUB, at the Business Development Academy, which will explain a bit the focus on business that I'll be having. But my entire project is funded by Sustain Brussels, and I'm working within that project. That is the Digital Innovation Hub, as Karel said, but more on that later. So I'll be touching the topics of digitalization in general, sustainability, how we look at it, and then making the connection between the two. Yeah, let's go. So, as you all know, we're currently, according to some people, in a fourth industrial revolution. So after the arrival of the steam engine and the mechanization of a century or two ago, we then had a new second industrial revolution powered by electrification, by oil as a new energy source, followed by an industrial revolution where information systems led to the possibility of advanced automation. And then now we would be in a fourth industrial revolution, characterized by mainly a set of technologies that are being applied and the way these technologies are interacting. So we're having a new way that technologies are smartly interconnected, humans and technologies. So you would have cyber-physical systems, you have an Internet of Things, and these technologies are able to communicate with each other in ways, for instance, that a technology could say, hey, I need a repair part here. So yeah, a level up there. Other technologies such as AR, augmented reality, virtual reality, additive manufacturing such as 3D printing, and all of this heavily intertwined with machine learning applications, with artificial intelligence applications, make that, yeah, we're entering for sure an interesting time in this industrial timescale. But yeah, if it's really a new industrial revolution, well, it might be a political statement until a certain point. According to some, this new Industry 4.0 is more a positioning of Germany within as a leader in this industrial landscape. But I mean, the innovations that are occurring are definitely clear. So whether or not we can call it a new time frame is up to debate. But so in Belgium, we see in businesses that I'm connecting with, that we with Sustain Brussels are connecting with, already huge leaps in terms of adopting these technologies. So AI in 2022 was adopted by already 10% of Belgian enterprises to a significant extent. But with generative AI advances, this of course, well, if you count adoption, the use of generative AI by certain employees, well, then this number will probably be much higher already. Many businesses are experiencing a digital imperative, as it's called, so they feel obliged to adapt their business model towards including these advanced digital technologies. And they feel this because of new technologies that may be disrupting the core of their business model. Competitors, I think in many sectors you see this, competitors which are very digital, which make use of digital platforms, for instance, which are arising in the landscape, and customers which want some digital aspects to buying from the company to appear. But the digital imperative for many businesses is more a gut feeling. We have to change with it. It's sometimes more a bit of mimicry, but yeah, it is experienced by many companies. And yeah, in terms of new business models, so we see in certain sectors that there has been a complete switch in how they perform their business. Think of the music industry, where we saw this move from analog to digital formats in their products. But even traditional industries such as banking or legal firms, or you name it, are changing in their core towards a more digital nature. All right, that being said, the focus is of this talk a bit more sustainability, to discuss that in relation to digitalization. And when talking about sustainability, well, naturally, or almost always, you start with a bit about climate change. So that's like perhaps the thing that feeds the sense of urgency most when it comes to we need sustainability. So here we have equally obligatory graph showing the temperature anomaly across the past 20,000 years. And for the past 11,000 years, we see that after a glacial period, we came into a relatively stable time called the Holocene. So the temperatures didn't fluctuate too much during this period of around 11,000 years. And that was actually very helpful for us as humans, because this predictability of temperatures made that we could predict food outcomes a bit better. And yeah, our current, well, the technological process that we experienced then, the changes in our societies were to a large extent thanks to these relatively stable surroundings. And then at the end, you see the little red line indicating how in a mere 150 years, we already changed more than 1.2 degrees Celsius. So I think to the reference period of 1850 to 1900, 2023 was already 48 degrees warmer. It's perhaps a bit of an anomaly, but I mean, it's very significant how hot the past year was. With a little news article headline I added, where the 10 last months were all, well, globally speaking, all record temperatures. This might decrease a bit more later. This is a heavy discussion among climate scientists. But yeah, the reaching or remaining below 1.5 degrees Celsius is a bit, can be deemed a bit challenging, even though it would still be possible. So if we have the temperature increase I was just talking about, that's actually only one factor of sustainability. The linkage between our carbon emissions or other emissions and climate change is just one factor within the sustainability story. For instance, we're in the midst also of a biodiversity crisis, where actually the terrestrial biosphere, well, the same for every other biosphere, is heavily under pressure of human impacts. And you don't have to read the axis there, but you just see the inclination of impact that happened over the past 150 years. We see the same for instance, water exploitation across the world. And even for non-natural impacts, well, here you have urban population, but the impact from cities on their surroundings. There are a lot of impacts occurring since 150 years that are increasing, and some scientists call this the Great Acceleration, where in terms of human impacts after the Second World War, we increased massively in our impact. And I just show this here because I want to emphasize, and that's maybe the main point of emphasis, is that when we're talking about sustainability, we're not talking about one factor, we're not talking about two factors, but ideally we're talking about a lot of them and very context specific which ones to take for when you're developing a technology and looking at the sustainability of it. A first good definition or commonly accepted definition of sustainability was in the Brundtland report, if you heard about it. In 1987, Gro Brundtland, who was previously the Prime Minister of Norway, led a commission for the United Nations where she provided the definition: sustainable development is a development that meets the needs of the present without compromising the ability of future generations to meet their own needs. That was the first way, a commonly agreed way to look at what sustainability now really means. We are not taking from future generations and their potential to meet their own needs. One of the important things about this report and this definition is that we still acknowledge the need for development. We still acknowledge the need for progress, because there are people who still don't have their needs met, but we look at it within a sort of finite planet point of view. Some key principles of sustainability are this equity. Well, one of the key principles is equity. And so this equity is intragenerational, us versus the future generations, but also between geological areas, geographical areas, and even, according to your definition, among species on this world. It's also dynamic. So actually, if you say this thing is sustainable that you have, well, you're not really acknowledging at that point that every technology or every whatever society is operating within a very dynamic system. So something that's sustainable now may not be so in the future. Sustainability is a process. It's not an end state in itself. It's also integrated, so there are a lot of sustainability factors, as we already saw. And between these factors, there are trade-offs, and it's important to acknowledge that such trade-offs actually exist. And then finally, it's value-driven. So a lot of sustainability factors, they need hard data to come to a conclusion whether or not something is sustainable. But a lot of things are actually very much, have a very large normative dimension, where depending on the stakeholder group, something would be sustainable or something not. I can have a production plant somewhere and the neighbors might not agree with my statement that the production plant next to them is sustainable, just to show the normative dimension here. But so yeah, a general way to look at sustainability is through 3 pillars or 3 parts of the system, being the economy, which is nested within society, which is nested within the broader ecology. And through these 3 pillars, you could distinguish then the parameters for sustainability. All right, so I just like this example to show a bit the complexity of sustainability when it comes to technology. Because it's never as easy a thing to answer, is a technology sustainable, as you would like. So here, in this example, a group of engineers were sent to the Usambara mountains in Tanzania. And they came there because there was a big problem with the fires that the inhabitants of this region were creating. So they had little fires in their houses. And these fires, they were burning on charcoal from the local forests. So these inhabitants were cutting massive amounts of forest next to their villages. And it were open fires. So there were huge health issues with the open fires in these houses, respiratory diseases and so on. So these engineers came there, okay, we're gonna try to help these people. And they actually made a largely improved cooking stove working with wood chips, residue wood flows, and with the smoke being brought out of the hut. Also, it led to way less smoke inside and way less forest degradation in the area. Yet, it was completely rejected by the local communities. And this was actually due to a manifold of reasons. A smaller one was, for instance, that in these open fires, a lot of traditional practices were happening with these open fires, such as certain cooking rituals and so on. Another thing was that, and then we come to, for instance, social sustainability, that the act of gathering wood by the women of the tribes who were using this, the act of gathering wood was the only time where women could privately discuss certain matters. And when the wood was gone, these private interactions were gone. So this was for the women of the community a very negative advancement. And then something a bit bigger, the wood coming from these wood stoves was creating a lot of smoke in these open fires. And yes, it was bad for respiratory diseases, but something else it did was the smoke eradicated mosquitoes in the huts. So actually, after it, we saw malaria problems occurring within these communities, and they were very far from hospitals, etc., and couldn't get the right medication. So yeah, just an example to show how complicated it is to sometimes say, that's more sustainable than that, because you could account for a lot more parameters than initially thought. Okay, so if we have here a packaging robot, and we look at these economic, these social, and these ecological factors that add up to sustainability, well, is this then sustainable, for instance, if you would know that they increase the energy efficiency a lot of this robot? To some, this energy efficiency increase would already mean, yes, we made a sustainable technology. But then if you, for instance, notice that there are certain trade-offs in the materials, the metals that are coming to the manufacturing of this robot, we might see another ecological story here. I put another circle to the right. This is all fictionist, by the way. I did not do an analysis on this packaging robot. But then, of course, as everybody who works with robotics, I think, thinks about, is a replacement of, for instance, laborers. That might lead to, well, job loss, but actually might also increase inequalities on the work floor. For instance, I don't know, if the employees that are later hired here will be more of the software or operator, highly educated type of staff. So just to show here that sustainability can be seen as broad as you choose it to be, but sustainability is a huge topic, and it also depends who you ask. Well, if you would ask certain stakeholders like the community associated with this factory, it might be worse than if you would ask an NGO for environmental protection. Just as a topic there. And then, yeah, I wanted to touch upon this a bit because I read a bit also in a paper where Karel co-authored on robo-ethics, just to highlight that when it comes to the ethics of such robot production, that this is often heavily intertwined with sustainability, especially social sustainability, but it is still a different category. If you would look at the SDGs, for instance, ethical aspects are not very much mentioned, or the necessity of it not very much implemented in the Sustainable Development Goals of the UN. So yeah, it's still a bit of a different category, but of course matters such as privacy, responsibility, safety also have a social sustainability dimension. Okay, that being said, I'll now introduce a bit the work I'm doing currently for Sustain Brussels. So, being a digital innovation hub, there are a lot of companies coming to Sustain Brussels, and these are generally divided into two groups. And those are the digital actors, the digital by nature companies, which are sometimes a bit afraid of sustainability because they find actually that it hampers their growth, that it's actually just this damned requirement by Europe to look at these kinds of things, to report on these kinds of things. And then you have the sustainability actors, which are sometimes a bit hesitant to acquire digital technologies because they feel like it doesn't fit within their message of sustainability, as you bring in new metals, you bring in a higher energy use, you replace workers, whatnot. But we try to, within Sustain Brussels, actually look at a set of solutions that works for both. So digital solutions where the sustainability is taken into account. And this very much fits within the European strategy of going towards a green and digital future, the twin transition, as it's called. So I'm in part responsible for the sustainability dimension within Sustain Brussels. So I developed two frameworks together with colleagues, and these frameworks assess the sustainability of digital solutions being brought to us. One of these frameworks is for the technology adopters, and one for the producers of digital technologies. And we consider this three-pillar approach to sustainability. But because we're working with small and medium-sized enterprises, so not only local, but also they have to be pretty small for us to be able to help them for free. They don't have time, those business leaders, so we use very easy to use language, or the frameworks are easy to use with little jargon in the language, and very much not time intensive. And then we finish it up with guidance if they would need it, where, for instance, we have a dashboarding scheme implemented to be able to compare their performance, to do a thematic comparison. For instance, when it comes to their greenhouse gas, the mechanisms they have in place for that, or the implementations on their, the effects on their workforce, etc. So this is the general scheme of how we look at these things. So we have a digital technology, and then one framework looks at the effects of this digital technology within the business, for instance, within the workers of the company, within the business process, which would be efficiency gains, etc., and then within broader society. So that would be the indirect emissions, the implications on the society in a social way as well. And then our second framework looks at, okay, you're a tech company which is producing a digital technology. What are the impacts from your production process? Again, across the social, economic, and environmental pillar. All in all, this is very much not a quantitative story. We're not asking them for data on their emissions, but it's more an awareness thing. Are you keeping track of this? Are you collecting data on this? And increasing the awareness there. And then personally, so I'm also performing studies on frameworks for sustainable digitalization. And there I'm looking in literature, what exists in literature in terms of such frameworks and tools, what's missing in business, for which I'm conducting interviews with sustainability managers, and then we will end my project probably with a practitioner-oriented tool creation. So yeah, the general focus of my study is to see what tools and assessment frameworks exist and what should be created for businesses to digitalize more sustainably. So just to go a little bit more in depth, I'm conducting a systemic literature review where from a huge pile of papers, I found 16 papers which actually are presenting frameworks for the sustainable digitalization of business. So these papers really need to link strongly with business and have their focus on digitalization and sustainability. Yeah, and not view the potential of digital applications to increase sustainability. So you can apply digital technologies to increase your efficiency somewhere, and then they're adding to sustainability. But I want to see if a company is switching from paperless to Excel, what would be the sustainability impact in a holistic manner? So yeah, mainly from these few papers that I found, yeah, well, logically they are quite recent in nature, and these frameworks can be categorized, yeah, mainly as decision-making frameworks. But actually, we found a range from broader economic frameworks to maturity models and risk assessment frameworks as well. All right. In case that there are representatives from small and medium-sized enterprises in Brussels watching online or here present, we're having trainers. We're having training sessions, master classes on sustainable digitalization with a more strategic orientation. So what should you look at, or which tools can you use as a manager to increase the sustainability of digital when you're a company, or more technically oriented if you're an IT manager or a developer, or more technically oriented, how can we increase the sustainability of digital? And we're having a set of trainings in May and June. Perhaps it's something interesting. Oh yeah, it's for free for SMEs in Brussels. That's maybe important. All right, so that was my talk. If anybody wants to discuss this further, feel free to reach out, also on LinkedIn. I'd love to connect with you all. So thank you.
Thank you very much, Arjen. Any question in the audience? Otherwise, I'll kickstart with one. All right. One first question is, you've done a lot of literature review. You've also looked at a lot of the digitization processes for technologies, and you talked about technologies in general. Are there any pointers or indication for the field of robotics specifically? Did you find specificities of robotics in terms of also sustainability challenges? Can you share maybe some thoughts or things that you've discovered on that?
Yeah, so, well, robotics specifically, because I'm obvious to you also not an expert on robotics, but when it came in view for me, it's mostly in a context where an LCA was performed, a life cycle assessment on a robot, but then extrapolated to the entire business model. And that's maybe the only thing interesting that I would like to add, is that when you're conducting an LCA, something new that's pretty interesting is to actually take into account the entire business model that will exist around that product. There is a cool research group in Sweden which is looking at exactly this. I think it's called Business Model Lifecycle Assessment. And so if you would have a robot applied within a company, the outcomes of this robot within the company may be different than if you would conduct a life cycle assessment and look at the impacts on environment separately within your lab setting or so on. So that's something relevant. I'm sorry, I didn't really... other frameworks?
No, that's...
Yeah, I don't have any other direct connections.
All right.
But
okay.
Thank you.
Thank you. Any question? They're online. Oh, yes, okay. Thank you.
Your topic is the digitalization in businesses, and I was wondering, because I hear the term a lot, could you give like an example maybe? Because I'm not sure what exactly that means and how maybe close it is to also using robots, or is it more using AI and programs and software?
Yeah, well, it's actually, if you're talking about digitalization, you're talking about the entire range of technologies which you would consider digital technologies, so where there's this digital aspect to it. Robotics fits within that in the right setting, I assume, as well. I mean, it does fit within that. But it's everything from applying advanced machine learning systems in businesses to actually a business switching from paper to Excel. We consider that all within digitalization. But so yeah, from very advanced technological innovations to the smaller ones. Yeah.
All right. Then, yes, follow-up question.
And you said you talked to a lot of businesses here in Brussels. Did you encounter any that were thinking of using or installing some form of a robot in their process of digitalization, or did you kind of avoided that because your focus is not really on robots?
Actually, I didn't. No. From sensors to AI to, but robots as such, no. But of course, we advise them on increasing the sustainability of digitalization. But at our colleagues at Ciris, for instance, which is a technology platform for industry and for technological industry in Belgium, they will definitely encounter these kinds of questions much more. But us, no.
All right. Thank you very much. Then a little round of applause for Ariane, and then thank you. So 5-minute break. So. All right, welcome back. Thank you for being here, and thank you also to the people online. It is now my pleasure to have the very esteemed Naveen Tiwari. He's a Marie Curie Fellow, but also part of the whole BrIAS Fellowship. He's part of the Nanyang Technological University in Singapore, and he will be talking now about the smart polymers for soft and wearable electronics. If you have any question, please write them down or note them down on a small piece of paper, and we'll then collect them for you. Thank you.
Thank you. Thank you, Carl, for your introduction. And I must thank, first of all, to the BrIAS event, where they have invited me as a junior fellow, because in this event, I can see there are diverse research field groups. People are working with this kind of things. I'm going to share some of my research field, which I work with the smart polymers for healthcare applications, mainly. And I'm also going to talk about some of the self-healing polymers where I have utilized for the flexible and stretchable electronics. So before I begin, it's a brief introduction about me, is like where I am from and what I do and what I have done in my studies, research, and all. So basically, I'm from India. A very well-known place is Varanasi in the north. This is my hometown. And I did my graduations in Ramakrishna Mission Vidya Mandir in Bengal. It is in the east side of India, where I did the bachelor's in chemistry. I did master's from IIT Kanpur. It's Indian Institute of Technology, where I did my MTech. It's Master in Technology in Material Science and Engineering. Then I moved to Singapore for my PhD, where I did work with the self-healing polymers for flexible electronics in School of Material Science and Engineering. As a first postdoc, I worked with the wearable sensors for analyzing the bioanalytes present in our body. And I did it in National Tsinghua University in Taiwan. Then I moved to Penn State because I have a lot of movement from here, because I did 1 year in Taiwan and then 1 year in Penn State, where I worked with the laser-assisted materials for stretchable electronics, where we worked with ultrasonic sensors as well. And then finally, I got the Marie Curie and I left Penn State and I moved to Spain. Right now, I'm in Spain as a Marie Curie Fellow in University of Santiago de Compostela. So this is a kind of overview introduction of mine. So today's presentation, I'll be talking about some of the backgrounds and introduction of wearable sensors, stretchable physical sensors, and also about some of my research work on smart polymers, self-healing polymers. Also, I'll give an example of bio-inspired materials for biomedical applications and wearable pressure sensors as well. Let's begin with the thing nowadays everyone is working with is Internet of Things in smart healthcares. If you have seen, a lot of people are working with this kind of sensors which we can attach to the human bodies for measurement, for doing a lot of smart healthcare applications. Can monitor the physiological and clinical parameters like glucose, blood pressure, temperature, and many more. So these sensors are, if you can see the, I can say that the growth of these sensors from then, previously it was like connected to smartphones. Now people are making these sensors which can directly attach to your body. And these kind of sensors, you can get a lot of information from your body like calcium, potassium, many more, glucose, lactose. Even people have these ear lenses where they can analyze the tears from your eyes, what kind of chemicals it is present if you have a person suffering from some of the eyes problems. So there are a lot of applications of this kind of IoT-enabled sensor systems. So generally, why we need skin attachable, this kind of pressure sensor patches? Because if you have seen the smart watches from many of the companies, they are non-invasive, but they have a very limit of detection, which you cannot detect with those kind of gadgets. So that is why the patches, which gives you non-invasive as well as, and can monitor those signals which you cannot get from the gadgets, which you just put it like a wristband. And the patch has a very high signal noise ratio, which is a very good parameter for the sensors application due to the conformal contacts with the skin. And this is one example where Samsung has already launched such kind of patches for healthcare applications. Now, what can be measured by this skin attachable sensor patches? So there are a lot of things. We can have this kind of sensors where you can have a biopotential electrodes, temperature sensors, strain sensors, humidity sensors, biosensors. And these sensors can measure the parameters like you can have like ECG. You can see there are a lot of examples, and this is just a part of it. And if you can see, people are doing a lot of research on this kind of thing as well. And the samples you can see where they can take the samples from the skin, stress, then from the order of your body, sweat, fluids, and there is one most important parameter is ISF, is interstitial fluid, which is beneath the skin, which gives the exact what is the content of present in your body. So people are also focusing on that kind of things, which can be like a microneedle based sensors where you can just have a little bit of pressure and then it can extract that liquid from your beneath the skin, and then you can detect it and get the exact parameters like of glucose and lactose. So there again, this is an example of stretchable sensors where people have done a lot of research, UV sensors and all. This is just an example to show you all. Coming to my work, I work with some self-fillable polymers where the self-filling polymers has a great opportunity of, like, if you see this graph, there is a thing in the y-axis is the performances. If you have an ideal material which can break down and after that you cannot reuse it. But if you see the performance in terms of time, if you see the performances of the ideal material, it fixes, and then after that, after time, it does not behave. But for the self-filling materials, is like you can regain the properties and again, and you can use it for many times. The self-filling materials have people use for sensors and electronics applications, smart motion control as well, and that damage detection and healing control, and autonomous self-filling soft robots. People have used for soft robots here in VUB. The group from BRAM, they were the first guy, to the best of my knowledge, they produced the self-filling soft robots from this polymer. Not from this polymer, but a class of polymer of self-filling. So this is one of my example of my self-filling polymer, is that we have derived this. I think there is a video. Yes. So this is a self-filling, this is a real-time video. We have a cut, and then after the cut, we apply some voltage, like around 6 volts, and within 2 minutes, the whole cut disappears, and the polymer gets self-filled. So it's a real-time video, how you can understand because of the shakiness of the hand. So yeah. So after 2 minutes, you can get a complete healed, and then you can use it for lot more time, and we have a multiple cut on the same location, and it heals back again. So how do we fabricate these healable electrodes? We have a glass substrate, and then we coat our polymer on the top, and then after that we dip it inside an APTS solution, because my polymer is like is a hydrophobic in nature, to make it hydrophilic, where we can attach the electrodes on the top of it. So I dip it in an APTS solution for 24 hours, and then I spray coat silver nanowire to form an healable electrodes. And this healable electrode we have characterized for many things. Physical characterizations is like the transmutations, the bending test, as well as the peeling test, where we can see the robustness of the electrode. After that, we have utilized this healable electrode as a transparent, flexible heaters. where we have characterized the heater characteristics of on and off, where we can hit the heater and then when switch off, it cools down. We have demonstrated this heater for defogging of goggles, which is useful in the cold countries where you wear a goggle and then the snow or it becomes foggy. And if you have a smart transparent attached to the glass, you can switch a very less amount of voltage, like 1 or 1.5 volt. You can defog the glass and you can use it for long. So that is the practical application of the heater. And then because in this previous work, the healing temperature was around 120 degree. So what we have done, we have added ionic liquid in the polymer as a plasticizer, and we could have reduced the healing temperature by half. Like now the healing temperature becomes 60 degree, just adding 50% of ionic liquid in the polymer. And also, if you can see that, the orange curve, even the black one is the normal healing polymer. It has a stretchability of just a 17%, but when we add this ionic liquid of 50%, it stretched up to 100%. It also improves the flexibility of my polymer as well. If you see the healing temperature, it was 120 previously, and later it becomes 60 degree. We did not change the healing time. The time was fixed 10 minutes. So, and we also see that the, the stress strain curve of healed samples, and the healing efficiency was around 92.6%, which is compared to the recent reports, literature reports. Here is one, I think, yeah. We have fabricated a self-fillable electrode. You can see this time the healing is very fast. We cut it, and the lights goes off. And suddenly, after a few seconds, the lights get on, and then we cut it in the same location. But when you cut in the same location, the healing time also gets increased. So it was not in few seconds, now it becomes like 2 minutes. So if you do a multiple cut on the same location, the healing time will increase for sure.
Same with humans, it works too.
Yeah, if you have a cut on the same location, yeah, that makes sense. So yeah, it has restored the connection. So from this, we have fabricated an alternating electroluminescent device where we have fabricated, and this electroluminescent device, when we mix the phosphor inside the polymer, still the phosphor mixed, the material also gets healed. You can see there is a gap, and when it heals, you can see the clusters of nanoparticles combining together in the healed section. And the luminescence was around 18 candela per meter square, which is also comparable to the literature. For this, I just show you the flexibility test of my device. Is like we have a electron, and the most important thing is when I'm bending it, you don't see the deterioration in the intensity of the device. So that is what we need for the flexible electronics. We have tested on different standardized cylinders for 20 mm diameter to 6 mm diameter. The more you lower down the diameter, the more you bend the polymer. So that is the criteria of testing on this kind of cylinders. Moving from this self-healing polymers, I've also worked with the bio-inspired materials where we have mimicked the shark skin because this is also very hydrophobic in nature. So we mimic this shark skin on a polymer. It's called EcoFlex, which is also a class of a PDMS polymer. When we had this structure, you can see that without structure, the electrode does not, it sticks with the polymer. And with the structure, when we press, it does not stick to the structure. So then we generate a kind of triboelectricity, which is also a sustainable form of energy, where you don't use any coal or any power, you just generate by mechanical harvesting. So what we have used this kind of sensor to analyze the gait analysis. It's like a movement of a human being when they walk. So Yeah, I think there's a video. Yes. So this is the polymer where we mixed the liquid metal inside it, and you can see that liquid metal encapsulated between the EcoFlex, and we can stretch up to 100% without any fail in the connectivity. There is another video where we have shown the multiple channel of real-time gate detection. It's like when we have these sensors on the foot, you can see the signals. And these signals are being taken from the 4 points, I forgot to mention here. These 4 points has the most impact when you walk. So we put the sensors on these 4 points, and we did the analysis. And this project was also collaborated with the hospital, where people who have a problem with the knee, so doctors recommend them and monitor them for a long period. And whenever they need the doctors or additional checkup, they can directly go to the doctors and check up. So they don't need to visit every time to the hospital with this kind of sensors. Next one is the wearable pressure sensors, where we mix the MXZine tissue paper for wireless human health monitoring. So this is a very simple and easy making sensors where we do a lot of human health monitoring, like running, touching, and you can measure the pulse rate as well. You can see there is at the end, we have a standing, walking, and jumping. You can have the signals, so we can monitor the wireless human health monitoring from this sensor. There is a short video, because in our work, if you don't present a video, then people are not going to believe it. So this is very clear, even for the paper as well. So that is why I put a lot of videos. So if you just see, he just places on the sensor, there is a bump in that, and once he removes, it comes down. So this is kind of a wearable pressure sensor. Yeah, the next one is again pressure sensors, which is based on the laser-induced gradient, which I worked in Penn State, with a micropyramids, where we form this kind of structured PDMS with the laser, and then we have another electrode with the ITO-PET, and then when we press, we can get the change in the capacitance of the sensors. And this change of capacitance we measure in terms of a sensor. So we have done a long-term cyclic test for like 4,000 cycles, and it shows a better performance. It still shows a good performance. And we have also tested the same, we have fabricated 3 samples with same condition, and we found that the parameters which are like is same. So that means we can plot a good error bar when we plot the data. So if we have 3 samples of same functionality, it makes sense that your sensor is working. We have also shown the applications of inotronic pressure sensors. We can measure the heartbeat from here, because the beat from the pulse of your finger or thumb is very low. So it represents the sensitivity of our sensors. When a person is just like in a rest, you can see the heartbeat at 68 beats per minute, but when he or she do any exercise, the beat rates increases from 68 to 104 beats per minute. We have also designed a smart, weighing scale, where with that, where we tested some of the lab members with the different weights, and we can see that when the weights increases, the sensitivity in terms of the capacitance also increases, which is correlate with the kg, with the weight. So if you see this, the black one is also increases when the weight increases, and the weight also increases from there. So the most important or the selling point of this work is like in an ocean. If you have an ocean and if you drop a glass of water in the ocean, you don't even feel, the ocean does not feel anything. That comes with the sensor is like when we have like 90 kg people sitting on this chair, and if you drop a 5 gram of pin on 90 kg, does my sensor is going to sense that? And the answer is yes. So if I drop a one pin, it shows some signal. That means if a person having a high weight, and if you want to have a sensitivity of, let's say, 1/10 or 1/9 or whatever in the ratio, still our sensors can sense the drop of the pin, and it can show the change in the capacitance. So it means the sensitivity of the sensor is really good. We have also incorporated this sensor on a human robotic hand interaction, where we can grab some things and we can feel the change in the capacitance as well. This is a small video. So there, if you can see, I think somebody is going to drop some pin. Yeah. So you can see that there is a change. So this is a live demo, and these are my colleagues where we are working in Penn State. So perspective of today's talk of mine is like, we need to put efforts towards the improvement of the stability and reliability, because still nowadays this kind of sensors is having a problem with stability and reliability for sensing. And also researchers are thinking more of nanomaterials required for the real applications. The sensor integrated system for combining communications, energy, and samples need to be developed for considering the specific needs. And the most important part is that collaborative research is essential for the success of this kind of field. Yeah. Finally, I thank to all my supervisors, group members, families, and friends. And I also thank VUB, Prof. Bram, and Sepe, who has invited me for this event. I also thank all my collaborators. Recently, I'm also working with Tecno de Montera and VUB. Here we are working with nanomaterials for biomedical applications for antibacterial properties. So, yeah, thank you. And you know that in the BrIAS event, without advertising, nothing happens. So I just want to advertise something, like I'm also acting as a guest editor for one of these polymer journal. So for the smart polymeric materials for soft electronics. If you guys have any paper, or just please let me know. Thank you.
All right, thank you. It was really interesting. Any questions in the audience to start with? All right.
This might be more a technical question, but you mentioned lenses in the beginning, and then later you had your own project, I think, with wireless sensors. Is there like a Wi-Fi, or how do the sensors
Okay.
translate transmit the
it's like
data?
NFC connections. So we have a wireless. We attach this sensor and we integrate a module with the Arduino board, Arduino board. And then with that, we can also design some apps on the phone where we can monitor this kind of thing. So yeah, it's like that.
Okay, but how's the transmitting from the sensor to the, like if it's a lens, how does it transmit?
No, we did not do the lens. Lens is done by some other person. Okay. I just gave an example of lens.
Yeah. Thanks.
Basically for the lens kind of thing, they do like for electrochemical sensors, where they gathered the tears from the eye. There is a well, and they collect like microliters of the tears, and then from the lens, they take it out and do analysis. Our one is like different, is a wireless, where we connect some Arduino boards and this kind of stuff to the programming. When we, like, let's say when the guy who was moving with the sensors, that was connected with some wires, and then we get kind of the signals in the monitor or screen.
All right, thank you. Any other question? Yes.
All right. Thank you for this very nice talk. As a former ICU nurse, we work a lot with sensors, and one of the biggest problems is sweat or low perfusion in the skin. Mm-hmm. I'd be interested to know if your polymer had a different relationship with sweat on the skin, and if the measurements were not affected by that.
Okay, so generally for my polymer which I have worked, for the self-healing polymers, I have not tested that sweat and thing, but people do analyze the sweat where they have the lot of the information available in the sweat. So they have basically they do with the electrochemical sensors. So what they do is they have a microfluidic channels where they do exercise and then they generate a sweat, and that sweat goes to the polymer through the microfluidic channel and collected in a well. And from that well, they just dip into the electrochemical sensors. It's like a strip, and then you can get the signals of glucose or lactose or whatever you want. For my polymer, I did not do, because my work was for flexible electronics, where I was working with some kind of soft robotics kind of stuff.
Okay, I like your presentation. Thank you very much.
Thank you.
And I think most of your, well, the sensors that you're showing, most of them depend really on the formation, and that also affects capacity.
Yes.
Okay. Do you use, just out of curiosity,
Yeah.
do you use also the type of, let's say, like piezoelectric effects and
Okay.
that type of thing?
Okay. Yeah. I know that because there are three forms of people have done, like piezo, then thermo, and tribo. So these three kinds of bit, but we do more kind of capacitive or this kind of stuff. But there are sensors where people use for thermoelectrics, triboelectric. I do also do the triboelectric, but piezoelectric also people do. So, but we don't do. But in future, I will surely do with the piezo, because they have a better performances as compared to the other sensors.
All right. Yes. So talking about sustainability, is there a way to make these marvelous sensors out of, I don't know, like biodegradable materials or things along these lines?
Yes. People still work with the biodegradable polymers because the work which we show, like the one I showed with the paper one, where the paper strips can be used for the sensors as well, where you can remove the electrode from the top and then just discard the paper. But there are biodegradable sensors. I don't do specifically, but other people are working with these biodegradable sensors where they have used this kind of biodegradable for making the, how do you call it? For old peoples, you put old people when they sleep at the night and they spill the liquid from their body, so they have diapers. So they form the biodegradable diapers where they can throw and degrade it, because that is also creating a lot of pollutions in the society as well. So people are, not only the old age people, but also the kids, buy a lot of diapers. They are already available in the market with the biodegradable diapers where they can degrade it in 3 weeks completely. So this kind of still research is there. I basically don't do, but people are doing this kind of stuff.
Any other question? Yes?
So the self-healing, is that for increasing the durability of those sensors? Is that the idea? Or what's
Yes.
Okay.
The thing is, even if you have a self-healing polymers, the best part of self-healing polymers, nowadays people are also getting the biodegradable self-healing polymers. So that has a sustainability factor as well, and that one can be used for longer time. So if you have a sensor, it cuts, something happens to that, it again regains, and it will show, till now, to the best of my knowledge, what I can say, it cannot show 100%, but it will also not show 50%. It will show around 90 to 100%, which is still enough for using the material, reuse it for more and more time, so that we can generate very less electronic wastes, which is going to be a major challenge in next 10 years or 15 years for sure. The way we are using it, the electronic materials, is going to be, that is for sure.
I think there is no better way, like finishing on this big sustainability challenge ahead of us. A round of applause, please.
Thank you.
On this note, thank you all for coming today. Thank you to Anya, Andres at the technical and organization. Thank you also, Michel, for the help today. Please register for the forum events, spread the good word, and see you next week.